Greeting. Welcome to the lecture of Introduction to Power Engineering. In this lecture, we will discuss about the microgrid definition, configuration, and application. A microgrid is defined as a group of distribution energy resources, including renewable energy resources and energy storage system, plus loads that operate locally as a single controllable entity. Microgrid can be found in both low and medium voltage operating range, typically from 400 to 69 kilovolts. Also, they exist in various size. They can be large and complex network up to tens of megawatt in size, with various generation resources and storage unit serving multiple loads. Microgrids can also be small and simple systems in the range of hundreds of kilowatt, supplying just a few customers. Microgrids have multiple possible configuration depending on their size and functionality. Thus, they exist in both grid-connected and isolated form. Grid-connected microgrids have a point of interconnection, abbreviated as POI, or point of common coupling, abbreviated as PCC, with a large power network and should be capable of seamless transition to islanded mode. Note that the islanding capability of microgrids combined with their ability to black start increases the resiliency of distribution system in times of emergency or blackouts. Isolated microgrids have no PCC, thus islanding is not an issue in these systems. A generic microgrid configuration is shown in the diagram, where the system is connected to the main grid via the PCC breaker shown over here and consists of common components such as load, various dispatchable and non-dispatchable distribution unit energy resources such as wind, PV, and synchronous generator, and ESS, which is representing the battery system over here. As seen in this diagram, a microgrid typically contains a communication infrastructure between microgrid central controller, abbreviated as MGCC over here, switches, components, primary control, and metering devices. Depending on the upper grid requirement and topology, there may also exist a communication pipeline between the MGCC and our terrestrial control layer. Microgrid control system refers to the set of softwares and hardware that ensure microgrid operational stability, optimality, and reliability. Microgrid control systems implies that the required control function may be distributed among multiple components rather than being centralized in one controller. Core functions of microgrid control system includes maintaining the voltage, current, and frequency within the desired range, keeping the power supply and demand balanced, performing economic dispatch and demand side management, and transitioning between various modes of operation. As seen in the diagram, the microgrid control system can be categorized into three hierarchies, namely primary, secondary, and terrestrial. Microgrid stability is dominantly defined by the primary control. This control hierarchy pertains to the fastest control actions in a microgrid, including islanding detection, voltage and frequency control, and power sharing and balance. Several architectures have been proposed for microgrid primary control system, including both centralized and decentralized approaches. These architectures depend on the microgrid type and purpose, including factors such as grid connectivity, type of grid forming assets, and required reliability level. The main variable used for primary control in a microgrid includes voltage, frequency, active and reactive power flow. In grid-connected mode of operation, voltage and frequency are mainly imposed by the main grid, limiting the microgrid role to perform ancillary services. The problem of stability in grid-connected microgrids mainly consists of the stability of individual components such as a particular distribution energy resources or of a sets of local loads including electrical motors and their impact on the system. Isolated microgrids are expected to play a significant role in smart active distribution grid. In this case, the system voltage and frequency are no longer supported by the main grid, and different distribution energy resources must maintain these variables in acceptable range. Due to the microgrid unique intrinsic features and systematic difference, operation in a standalone mode is more challenging than in conventional power system, facing particular stability and system adequacy problem. Primary control in microgrids with grid-forming synchronous machine is considerably different than inverter-based system, making stability studies an issue different for each operating paradigm. For example, synchronous machine perform voltage and frequency control and power sharing using conventional exciters, governors, and the machine mechanical inertia. Inverter-based distribution energy resources rely on a set of fast voltage and current control loops along with the phase load loop, and thus there is no mechanical time constant involved in the control process. Thus, inverters can be designed to emulate the inertia of a synchronous machine via appropriate control. The nature of the stability problem and dynamics performance of a microgrid are considerably different than those of a conventional power system. Since the microgrid system size is considerably smaller than that of a conventional large interconnected power system. Microgrid feeders are relatively short and operated at medium voltage level, presenting a lower reactance to resistance ratio compared to conventional system. As a result, the dynamic performance of microgrids and the mathematical relationship between voltages, angle, and active and reactive power flow are different than in conventional grid. Another consequence of the microgrid small size is higher uncertainty in the system due to the reduced number of loads and highly correlated and fast variation of available renewable energy sources. Demand-supply balance is critical in microgrid, and hence the intermittent nature of renewable energy resources is particularly relevant in these systems. Bidirectional power flow between generators and prosumer are also an issue due to associate complication with control and protection coordination. In addition, since electrical power is supplied by electronically interfaced distribution energy resources and relatively small synchronous machine, system inertia is considerably lower in microgrid compared to conventional power system. A significant concern in Icelandic grid microgrid, especially in remote communities with small distribution system, is their relatively low short circuit capacity. In such system, a small change in the microgrid configuration, such as Startup or shutdown of a diesel generator can result in a relatively large voltage and frequency deviation. This poses stability challenges when operating conventional synchronous generators and inverters interface power generation resource together, since perturbation in this case may lead to inverter shutdown. Unlike conventional power system, loading in the microgrid is typically unbalanced, which can be as significant as 100% between the three phases. Operating microgrid under such significant unbalanced condition may jeopardize system stability and requires techniques that are designed to handle these conditions, such as the use of four-leg voltage source converter. In addition, traditional stability analysis technique and models assume balanced operation and therefore are not valid in unbalanced system. The most important difference of microgrid compared to bulk power system relevant to stability are the followings: smaller system size, higher penetration of renewable energy sources, higher uncertainty, lower system inertia, higher R by X ratio of the feeders, limited short circuit capacity, and unbalanced three-phase loading. Rising cost and burden of transmission and distribution infrastructure means building new transmission and distribution infrastructure has become difficult in some areas due to permission issues, public resistance, and the difficulty, cost, or both of upgrading or building new infrastructure. Second reason is the integration of the renewable and storage technology. That is, the greatest obstacle to the integration of renewables has been the risk to grid stability. Some renewable energy resources, most notably wind and solar, are intermittent by nature, which increases the voltage and frequency fluctuation on the grids. The risk is greatest when there is a high penetration of renewables. However, technology advancement in grid stabilization and energy storage have addressed these concerns in microgrid. Nowadays, the challenge of the renewable energy generation peaking not matching up with demand peaks can be resolved using energy storage modules. An energy storage module is a package solution that stores energy for use at a later time. The energy is usually stored in the batteries for specific energy demand or to effectively optimize cost. The modules can store electrical energy and supply it to the designated loads as a primary or supplementary sources. Moreover, it provides a stable and continuous power supply regardless of the supply source status. Voltage and frequency regulation can also be improved by using storage modules. Power quality and reliability is the third reason why microgrid are under consideration. The need for high reliability and good power quality has increased as more customers install microprocessor based devices and sensitivity and use machine. Public policy is also a driving force for a microgrid development. In a full reversal from the past, public policy today is favorable and favoring distributed generation that offers improved efficiency, lower emission, enhanced power system security, and other benefit of national interest. Policies supporting this includes tax credit, renewable portfolio standard, emission restrictions, grants, and so on. Another reason of microgrid concept is more knowledgeable energy users. That is, energy users are becoming more aware of alternative power approaches and are more willing to consider on-site generation options than in the past. Many are interested in combined heat and power as well as reliability enhancement. Storm recovery and restoration is another issue solved by the microgrid. Hurricane Sandy and other superstorms of the last decade have highlighted in painful and expensive way the need to protect consumers from the devastation caused by such natural disaster. Today, both utilities and industry recognize the need to collaborate to make the microgrid a reality and ensure our community, place of business, or entity is insulated from an extended power outage in the case of a natural disaster. The technology needed to make microgrid feasible for everyday use, such as that needed for power storage and stabilization, has reached a point where it is commercially viable and available. The reliability benefits of the microgrid are clear. When the main grid loses power, the microgrid can switch to island mode. As long as there is an adequate source of power at the local level, for example, diesel generator, wind turbine, fuel cell, and photovoltaic, etc., the power continues to flow while the rest of the community is enveloped in darkness. Increased interest in security is also a main contribution factor why the microgrids are important. While cyber attacks often dominate the discussion of grid security, utilities and government needs to find ways to protect the grid from natural disaster as well as physical sabotage. Experts agree that any prolonged disruption of power, regardless of the cause, represents a threat to security and economic stability. This century is expected to witness unprecedented growth and challenges in power generation, delivery, and usage. Environmentally friendly, renewable, and clean alternative power generation technologies will play an important role in future power supply due to increased global public awareness of the need for environmental protection and desire for less dependency on fossil fuels for energy production. These technologies include power generation from renewable energy resources such as wind, photovoltaic, microhydro, biomass, geothermal, ocean waves and tides, and clean alternative energy power generation technology such as fuel cells and microturbine. Renewable energy generation sources often come in the form of customized distributed generation system in grid connected or standalone configuration. Fuel cells and microturbine could also be considered renewable power generation sources if their input fuel is obtained from renewable sources. For instance, landfill gas has been used to fuel microturbine. Biomass can be gasified into synthesis gas and used as fuel for microturbine and fuel cells. Or hydrogen fuel can be generated using wind or PV generated electricity through a electrolyzer for fuel cells. Though not renewable, diesel generator and reciprocating engine are also still commonly used for wide range uh, of power application, particularly in remote area and as backup energy sources in some standalone system such as a power source for a remote telecommunication tower. The diesel engine mature technology, relatively cheaper price, low fuel cost, and high fuel efficiency have kept diesel generators in the market. They are also reasonably fuel tolerant and can be considered renewable power sources when fueled by renewable fuels such as biofuel. In general, the key driver for the development of the above energy systems are their perceived benefit, such as reduced carbon emission, improved power quality and reliability, and in some cases combine heat and power operation, which will increase their overall system efficiency significantly. Because of the intermittent nature of many renewable resources, for example wind, solar, ocean wave, hybrid combination of two or more of their relevant power generation technology along with storage and or alternative energy power generation can improve system performance. For example, wind and solar energy resources in a given area are somewhat complementary on a daily and or seasonal basis. In general, hybrid systems convert all the resources into one form, typically electrical and or the storage energy into some other form like chemical, compressed air, thermal, mechanical flywheels, etc. And the aggregate output is used to supply a variety of loads. Hybridization could result in increased reliability. However, proper technology selection and generation unit sizing are essential in the design of such system for improved operational performance and dispatch and operational control. Different generation sources may also help each other to achieve higher total energy efficiency and or improve performance. For instance, a fuel cells microturbine combined cycle system can better utilize the energy available in the fuel to achieve a significantly higher overall system efficiency than either source can possibly achieve. Or the response of an energy source with slower dynamic response, for example wind or fuel cells, can be enhanced by the addition of a storage device with faster dynamics such as the battery bank, supercapacitor or flywheel to meet different type of load requirement. For example, slowly varying loads and fast load transients. Storage is an integral part of a hybrid renewable energy generation system. Capacity-oriented energy storage technologies such as pumped hydroelectric system, compressed air energy storage, and hydrogen storage generally do not have fast response time and are used for long-term energy storage release such as managing slow load variation. On the other hand, access-oriented storage devices with fast response times such as batteries, flywheels, supercapacitors, and superconducting magnetic energy storage are used for responding to short-time disturbance such as fast load transient and for power quality issues. The table gives a summary of different renewable energy power generation technology and different energy storage scheme which may be used in hybrid system. Any combination of renewable energy power generation technology along with proper storage and possibly combined with the conventional generation technology, example a diesel generator, could form a hybrid energy system. For example, a hybrid system could have any combination of wind, PV, microturbine, conventional diesel generator, conventional diesel generator, storage battery, and fuel cells, electrolyzer, hydrogen storage in grid connected or standalone configuration, often referred as to a microgrid. The output from various generation sources of a hybrid energy system need to be coordinated and controlled to realize their full benefit. Proper optimization technique and control strategy are needed for sizing and for power dispatch from the energy sources to make the entire system sustainable to the maximum extent, while facilitating maximum reduction in environmental emission and at the same time minimizing cost of energy production. Renewable energy sources have different operating characteristics. It is therefore essential to have a well-defined and standardized framework procedure for connecting them to form a hybrid system, or more widely a microgrid, where a local cluster of distribution generation sources, energy storage, and loads are integrated together and capable of operating autonomously. A robust microgrid should have plug and play operational capability. Adapted from the concept widely used in the computer science and technology, plug and play operation here means a device, a distribution generator, an energy storage system, or a controllable load capable of being added into an existing system without requiring system reconfiguration to perform its design function, namely generating power, providing energy storage capacity, or carrying out load control. A suitable system configuration and a proper interfacing circuit, also called power electronics building block, may be necessary to achieve the plug and play function of a distribution generation system. There are many ways to integrate different alternative energy power generation sources to form a hybrid system. The method can be generally classified into three categories: DC coupled, AC coupled, and hybrid coupled. The AC coupled scheme can further be classified into power frequency AC coupled and high frequency AC coupled system. In a DC coupled configuration, the difference alternative energy sources are connected to a DC bus through appropriate power electronics interfacing circuit. The DC sources may be connected to the DC bus directly if appropriate. If there are any DC load, they can also be connected to the DC bus directly or through DC-DC converter, such as shown over here. To achieve appropriate DC voltage for the DC load, the system can supply power to the AC load 50 Hz or 60 Hz, or be interfaced to a utility grid through an inverter, which can be designed and controlled to allow bidirectional power flow. The DC couple scheme is simple and no synchronization is needed to integrate the different energy sources, but it also has its own drawbacks. For instance, if the system inverter is out of service, then the whole system will not be able to supply AC power, such as if this inverter is out of service, there will be no energy in feed to the grid. To avoid this situation, it is possible to connect several inverters with lower power rating in parallel, in which case synchronization of the output voltage of the different inverters or synchronization with the grid if the system is grid connected is needed. A proper power sharing control scheme is also required to achieve a desired load distribution among the different inverters. AC coupling can be divided into two subcategories: power frequency AC coupled and high frequency AC coupled system. The schematic of a power frequency AC coupled system, which is abbreviated as PF-AC coupled system, is shown in figure A, where the different energy sources are integrated through their own power electronics interfacing circuit to a power frequency AC bus. Here power frequency means the desired frequency of the utility grid, such as 50 Hz or 60 Hz. Coupling inductor may also be needed between the power electronics circuit and the AC bus to achieve desired power flow management. The schematic of higher frequency AC coupled system is shown in figure B. In this scheme, the different energy sources are coupled to an high frequency AC bus to which high frequency AC load are connected. This configuration has been used mostly in the application with high frequency AC system loads such as in airplanes, vessels, submarine, and in space station application. Normally, the frequency is used as 400 Hz as a high frequency AC system. In both PFAC and HFAC system, DC power can be obtained through AC-DC rectification. The high frequency AC configuration can also include power frequency AC bus and utility grid through an AC-AC or DC-AC converter to which regular AC load can be connected. Instead of connecting all the distribution generation sources to just a single DC or AC bus, as discussed previously, the different distribution generation sources can be connected to the DC or AC bus of the hybrid system. The diagram shows a hybrid coupled system where distribution generation resources are connected to the DC bus and or AC bus. In this configuration, some energy sources can be integrated directly without extra interfacing circuit. As a result, the system can have higher energy efficiency and reduce cost. On the other hand, control and energy management might be more complicated than for the DC and AC coupled scheme. Different coupling schemes find their own appropriate application. If major generation sources of a hybrid system generates DC power and there are also substantial amount of DC loads, then a DC coupled system may be a good choice. On the other hand, if the main power source generator generates AC with reasonable power quality for the grid and the connected loads, then an AC coupled system is a good option. If the major power source of a hybrid system generates a mixture of AC and DC power, then a hybrid coupled integration scheme may be considered. It is worth mentioning that the power electronics interfacing circuit in AC coupled system and hybrid coupled system can be made as modular building blocks, which will give the system more flexibility and scalability. Component sizing of hybrid renewable energy system is an important task. Selection of the important and most suitable generation technology, that is suitable mixture of renewable energy and conventional sources for a particular application, is also equally important. Available application software can be used to properly select generation technology and their size for specific application. For example, with the aid of Homer software developed by the National Renewable Energy Laboratory, a hybrid renewable energy system can be designed. And with the aid of the distributed energy resource customer adaptation model software, optimum technology selection for hybrid system to operate and as independent microgrid can be achieved. Unit sizing and technology selection can sometimes be as straightforward as meeting certain simple requirements, such as using the available generation technology and not exceeding the equipment power rating. Or it can be as complex as satisfying several constraints and achieving several objectives to maximum extent at the same time. Normally, based on available statistical information about generation, load, financial parameter, geographical factors, desired system reliability, cost requirement, and other case specific information, generation technology and their size can be optimized to satisfy specific objective function such as minimizing environmental impact, installation and operating cost, payback period on investment, and or maximizing reliability. Power system optimization methods such as linear programming, interior point method, and heuristical methods such as genetic algorithm and particle swarm optimization can be used for component sizing and energy management of hybrid renewable energy system. These techniques are essen- especially attractive when multiple objectives are to be met, some of which may be conflicting. For example, minimizing cost, maximizing system availability and efficiency, and minimizing carbon emission. In today's lecture, we have overview the concept of microgrid and its structure. Today's lecture ends here. Thank you for listening.